Okay, let's look at some practice problems dealing with work energy theorem. Anytime that you've got work or energy mentioned in a problem, it's probably a good idea that you start with the work energy theorem. How much work is required to lift a 2.5 kilogram object to a height of 6 meters? How much work is what we want, so that's definitely going to be part of our equation. Do we use delta E or FD? Well, they gave us a distance. That's probably a clue that you're going to use force times distance and not delta E. Well, let's check and make sure. Can we get a force? Well, what force is doing the work? Well, we're lifting this object. What force are we applying? Well, we're applying a force that's equal to the weight of this object. And we can certainly calculate the weight because weight is mass times gravity. So yes, we use force times distance and not change in energy. How much work is done? Force is equal to the weight. That's the force that we're applying. So the force is equal to mass times gravity. And the distance we lifted is 6 meters. Well, mass times gravity times distance. So let's put in now, mass is 2.5, gravity is 9.8, and the distance is 6. And 2.5 times 9.8 times 6 will give you 147. Which is good because we got the right answer. Woohoo! Number 3, let's look at this one. We have a car, 878 kilograms, that's the mass. Skids to a stop across a horizontal surface over this distance, 45.2 meters. They give us the friction force acting on the car, 7160 newtons. Newtons is a force, you should know that. So first of all, we want to calculate work done on the car by friction. Once again, work equals change in energy equals force times distance. We want work. Do we use change in energy or force times distance? They give us a force, and they give us a distance. Pretty easy decision. Not change in energy. We're going to use force times distance. Work equals FD, which equals 7160 times 45.2, and I bet that comes out with something really big like the answer that's on there. 323632. That's how much work is done on the car by friction. Force times the distance. Which, by the way, again, if the car is skidding to a stop, friction did this much work, that means the car had this much energy to begin with before it started stopping. Okay, now we want to know the initial kinetic energy of the car. Now, you might be tempted to say kinetic energy, EK, equals 1/2 mv squared. It's a good idea. The only problem is, look at this problem. We don't know how fast they're going. We don't have a speed. So we can't use that. We got to do something else. Well, let's go back to the work energy theorem. Work equals delta E equals FD. Let's just start there and see what we get. Initial kinetic energy. Well, I know that change in energy is final energy minus initial energy, right? And I want to know initial kinetic energy. So guess what? That's what I'm looking for right there. And guess what I just found right up here? I found the work. So we can take this work and plug it in right here, and work equals final energy minus initial energy. So here we go. 323632 is the work. The final energy, we're coming to a stop, skids to a stop, so the final energy will be 0 minus E sub I. That's what we're solving for. We don't even need to know the speed. We know the kinetic energy. We will solve for E sub I, and you should get negative 323632 joules. Or no, positive. That'll be positive because you'll subtract that away. Okay, and that's what I just told you up here, that this is the energy that the car had before it started to stop. Notice that these two are the same. If those two are the same, they actually have to be the same according to the work energy theorem. And then C, we want to know the initial velocity. Well, we just found the initial kinetic energy right here. And if kinetic energy equals 1/2 mv squared, then we can solve for the speed. So, once again, plug in 323,632 for kinetic energy equals 1/2 times the mass of the car, 878, times speed squared. Let's see, 878 divided by 2 gives you 439. So 323,632 equals 439 v squared. Divide both sides by 439. So 323,632 divided by 439 gives us 737.2. And the last step we have to take is to take the square root, and the square root of that will give us 27.2. V equals 27.2 meters per second.